Hello everyone again. For those of you who have chosen to join in live, or for those of you who are checking out this episode offline on SoundCloud or iTunes, thanks for dropping in again. Sorry, I'm just going to give a bit of feedback here. Yes, thanks for joining in for our next episode. Today we're lucky enough to have Dr. Tom Wong, who has recently joined the University of Texas at Austin in their group on quantum algorithms and complexity theory. And so he's been gracious enough today to sort of sit down and have a bit of a chat about his work, his history, and what's happening now in Texas. So Tom, thanks for joining us.
You're welcome. Thank you for having me.
No, not a problem. As I said in the email beforehand, we sort of jump in and give a bit of a personal history to yourself, and what got you interested in quantum technology and quantum computing, and sort of what aspect of quantum computing are you looking at? Because you are a theorist. Maybe the best terminology is a quantum information theorist, and try to explain to people what that is and what aspects of this new field of technology you focused on.
Yeah, so a little bit about me. I'm originally from California. I went to Santa Clara University as an undergrad, which is a small liberal arts Catholic college, and actually triple majored there. So I majored in physics, math, and computer science. So there was already a part of me that really liked both physics and computer science. And so when I went to grad school, I actually wasn't sure what I was going to study, because I did go to a small school, and generally there aren't as many research opportunities. But I knew that there was someone who did quantum computing. And so after my first year of grad school, I sent an email to David Meyer asking if he had a summer project that I could do, because I was interested in potentially working with him. And he said, sure. And then that summer project turned into my thesis, and I enjoyed it. I stuck around, we got along well. And so,
so a summer project turned into a thesis.
Yeah.
It's like one hell of a summer project.
Yeah. So the idea that David Meyer had for me was to investigate the power of computation if you have nonlinearities. So it's well known that quantum mechanics is linear, of course. Mm-hmm. But nonetheless, there are certain many-body quantum systems that have effective nonlinearities. So one well-known example are Bose-Einstein condensates. Einstein condensates, under certain conditions, if you do mean field theory and do a calculation, what you find is that the effective evolution is given by the Gross-Pertevsky equation, mm-hmm. which is a Schrodinger type equation, but it has a cubic nonlinearity. And so even though quantum mechanics is fundamentally linear, one might wonder, if you have these effective nonlinearities, can you do computation more powerfully? Mm-hmm. Mm-hmm. And so we looked into that, into different forms of nonlinearities, and it ends up being really interesting from multiple angles. So one is just from a pure computer science approach, which is if you have a certain model of computation, how powerful is it? And so in this case, we expect it to be more powerful than quantum computing. How much? And the way we explore that is by looking at Grover's algorithm as a quantum random walk. And right. So we know that Grover's algorithm with quantum computing is optimal, that the square root of n is the best you can do. And so if you have a nonlinearity and you're able to do better than the square root of n, you know that the improvement you got is from that nonlinearity. Mm-hmm, mm-hmm. So it gives you a way to quantify the additional computational power that you have. If you search in the cubed root of n or the fourth root of n, you can kind of gauge how much more powerful the nonlinearities are. And so, from a computer science perspective, there's that aspect of just how powerful is a certain model of computation. But as a physicist, I think one of the big interests in it is precisely that, as you said, quantum mechanics is linear. Mm-hmm. So you can't actually do better than the square root of n. So if you are doing better, that additional speed up has to come from somewhere. There has to be additional resources that you're using. And in this case, for example, with the Bose-Einstein condensate, the additional resources would be in the additional particles that you need in order for the system to effectively evolve nonlinearly. It's only as you have many particles that this asymptotic behavior occurs. And so you can use the additional speedup that you get over Grover's algorithm as a way of lower bounding the number of particles you need in your Bose-Einstein condensate for, say, the Gross-Patevsky equation to be an effective equation describing how it evolves.
So are you talking about being able to sort of characterize the nature of your physical system based on how fast Grover's search is, or the other way around?
I guess you can look at it from both perspectives. If you see your physical system as fundamentally having that nonlinearity, then we showed how fast you can solve Grover's problem. Mm-hmm. But then there's the vice versa, is that if you assume that Grover's algorithm is the best you can do, then it ends up informing us on how many resources you need in your physical system. Mm-hmm. And so, it's not just these, wild nonlinear theories that we're thinking of. Like, there are actual physics applications to these.
So, I mean, a lot of people may have heard of Grover's algorithm in terms of the square root of n speed up. And you're saying in this particular case with Bose-Einstein condensates, you can get higher levels of speed up. What does this mean in terms of computation? Because, I mean, the square root of n speed up is indicative of a quantum computer working on qubits.
Yeah.
So how is this working? How would this work for an engineered kind of system if you wanted to take advantage of this?
Mm-hmm. So we analyzed Grover's algorithm by formulating it as a quantum walk or quantum random walk. And so you imagine that you have a quantum particle that's jumping around on a lattice, and that lattice is your database. So the vertices of your different lattice sites that corresponds to the different items in your database, and you jump around. And so, if one wanted to potentially implement this physically, like a nonlinear quantum walk, you would need a Bose-Einstein condensate. You trap it in an optical lattice or some type of lattice, so that way you have these different points, and then you make sure that your condensate is in the physical parameter regime where it evolves by the Gross-Patevsky equation. So you make sure that your trapping depth is a certain value, and the lattice spacing is something. So this is stuff that's worked out by a condensed matter physicist.
Right.
And you have to make sure you have enough particles that there's this effective nonlinearity. And then you just let the particle walk randomly as it normally would, just by evolution, by the Gross-Patevsky equation. And to make a search in this context, it'd be a form of spatial search. So you would mark one of the lattice sites. That would be your the oracle in Grover's algorithm. And the idea is that you're just trying to find this marked lattice site.
So, I mean, this sort of moves into certainly your work, but also people like you in general, is that this seems to be much more on the foundational side. There's sort of questions about, what is computation in this context, and what does it fundamentally mean to work with quantum mechanical systems? I mean, most of our guests are either people who are very much in a hurry to try to build these systems, to push this into a commercial marketplace. Your work seems to be much more on sort of the more fundamental questions as to what information processing is, what is quantum information processing. So maybe talk a little bit about this distinction about sort of practicality versus fundamentals.
Yeah. Well, I mean, there's a lot of people who ask why we don't have more quantum algorithms. And if you think about it, there's maybe only 4 general methods that we have for designing quantum algorithms. So there's algorithms that are based on quantum Fourier transforms, like Shor's algorithm. There's amplitude amplification algorithms like Grover's algorithm. there's quantum simulation algorithms like the linear equation solver. And then finally, there's quantum walks. And so if we think about it, quantum walks, they're one of 4 ways that we currently have for designing quantum algorithms. Mm-hmm. So, it would be wise for us to really understand how they work and what they can do and can't do. And so in some sense, a lot of my work has been on that, at trying to understand how quantum walks compute and how they do what they do. Because there are still very basic questions that we don't understand about them. And so, so even though I'm not working towards a very, concrete goal, like building a quantum computer that we can put to market, mm-hmm. I think, we're thinking about fundamental questions that are very important in understanding what we will do with quantum computers. And so I think my motivation is twofold. So one is that from an algorithms perspective, understanding how these quantum walks work. I think the other motivation is that, at least with a continuous time quantum walk, it just describes how a particle evolves by Schrodinger's equation when it's trapped in a lattice or a graph. And so this is really a physics problem of understanding how a quantum particle evolves or behaves. And so, if depending on the underlying lattice or graph that you walk on, you can explore different ideas that are much more in typical lines of physics. So for example, there's a lot of astrophysicists, I guess, who think about whether space-time is flat or if it's curved. Is it positively or negatively curved, or is it flat? Things like that. And so this is actually something that you can explore with quantum walks. So if you have a lattice, you can define positive and negative curvature on it and flat curvature, and you can see how the quantum particle will behave on that. And so depending on one's philosophical outlook on the universe, it could be that space is actually quantized, at least at the Planck scale. Once you get to that level, space is actually now in these.
So, you say in a philosophical level, but can these kind of ideas, these kind of approaches, give you more of a sort of a physical test bed? Can you start thinking about the idea of merging these questions in astrophysics with these questions in quantum information?
Yeah, I think so. One of the big challenges of modern physics is to come up with a quantum theory of gravity, and that is basically merging ideas of general relativity and curvature with quantum mechanics. And so I don't claim that what I just said earlier is quantum gravity, but
no, of course not.
To explore how quantum mechanics works on space at that level, I think is still interesting.
But I suppose it's these kind of questions: is how does information theory or quantum information theory start melding more so into broader areas of physics? One of the most probably interesting areas, or at least maybe one of the most well-known areas, is the melding of information theory, quantum mechanics, and general relativity through the information paradox, and the black hole information paradox. In terms of sort of how these things are starting to now intersect, especially from the standpoint of somebody like you who certainly works more so on the fundamentals, are you starting to see these sort of things coming in where it's not just people like us sitting in a room playing around with quantum versions of computers? We're now starting to understand more about the fundamental structure and the fundamental behavior of the universe through something as surprising as information theory.
Yeah, I think that's definitely a trend that we're seeing. Like, for example, in Waterloo this summer, they had the conference or the summer school. It was called It from Qubit, which you might have heard about, where it's basically getting physicists and quantum information people together, teaching them about each other's fields, and seeing what comes out of it, because like you mentioned, we are seeing a lot of physics being informed now through quantum information ideas. So like Scott Aronson here has done some work on black holes specifically, and how computational complexity, arises in that, and it's something that you need to look at. And so that's definitely a growing area where we see quantum information informing just areas that people would consider to be just pure physics.
Mm-hmm.
Yeah.
So, I mean, okay, you started talking about sort of your work with David when you were doing your PhD still in California, and then you sort of took a bit of a left turn and you went to Latvia, of all places, for your postdoc.
Yeah.
And then spent a couple of years there, and now obviously has come back to Texas.
Yeah.
So certainly what motivated you to go there, and in terms of the work that you were focusing on for the last couple of years before you moved back to the States?
Yeah. I think there's multiple reasons why I moved to Latvia. One is that just personally, I had never been to Europe before. I traveled to other countries and continents, but actually never to Europe. Mm-hmm. And I think a lot of Americans dream about backpacking through Europe and things like that. And so when I had this opportunity to move to Latvia, I thought, well, I might as well move there.
Most people not from the Baltic states can't point to the Baltic states. So
yeah, I honestly did not know where Latvia was until I met Andres and Linus, and we talked about a postdoc. So I had to look it up and think about what it would be like moving to a smaller European country. But I really loved it, actually. Yeah, and so obviously Andres is very well known in the theoretical side of quantum computing and quantum algorithms, and so for me, I read several of his papers in grad school, and I've known about his work, and so in terms of a postdoc, it was a great place for me. He's done a lot of work with quantum walks as well. A lot of the seminal papers have been by him, and so yeah, I wasn't sure what to expect when I moved there. I knew that Andres would be there, but I wasn't really sure who else would be there, how big the group was, or the university. But he's got a really big group that's thriving there. There's maybe 17 researchers, actually, which is far bigger. Yeah.
This is at the postdoc level or postdoc plus
students? There's say 2 faculty members, maybe 6 research scientists / postdocs, and then the rest grad students. Mm-hmm. But the point is, it's not just Andres. It's a huge group, and there's lots of people to collaborate with. And so there are a couple students I was working with that I have several papers with now that got into quantum walks and got to work together. And other people in the group have also worked on quantum walks. And so I thought that was a very natural place for my research to thrive in. Yeah.
So, I mean, the structure itself, again, sort of getting back to sort of these questions of fundamentals versus sort of practicality.
Yeah.
Do you see the stuff that you worked on, or Andres, or various others that you worked with over the years? Do you see this stuff sort of coming into sort of the devices that are being fabricated, the protocols that are being discussed, the machines that hopefully in the next 5 or 10 years are going to be built? How much does sort of this work that you focus on sort of creep in to this sort of engineering world of quantum technology?
Well, a lot of my work with quantum walks has explored what lattice structures or what graph structures and how these structures affect the ability for a quantum walk to search for information. So if you have, like I said earlier, a vertex that's marked by an oracle, mm-hmm. How quickly can a quantum walk search and find that marked item, depending on what graph you're searching on. And so it turns out that this is a very tough problem that is still open, that we don't have a general theory for, if I give you a graph, you can just look at it and be like, oh, like it'll be fast or it'll be slow. When I say fast, I mean, you'll search in Grover's root n, or slow will be no better than classically guessing and checking. Mm-hmm. And so I've been doing a lot of work with that. And, in some sense, there are fundamental and pure aspects to it where it's a combination of graph theory and quantum information and things like that. But there's some sense in where there are practical flavors that come out, because a lot of things that people are thinking about now with trying to build quantum computers is what architectures and how you want your qubits to be, how you want to connect your qubits. Like, are they, laid out in a 2D grid, or are they in a straight line? Things like that. Basically, the local connectivity of your qubits makes a difference. And so similarly, the spatial structure of your quantum walk makes a big difference. Mm-hmm. And so I think there's some sense in that the things that we're learning in terms of quantum walks on graphs could potentially be useful for the structures of qubits, or if we have, a big quantum network, like how will quantum information move on that network? Well, a network is also just a graph. And
so I mean, just to try and give us a bit of a handle on this, I mean, we have, walks versus quantum walks.
Yeah.
And quantum walks have turned into, as you said, one of the four generalized areas about how a quantum algorithm works. When you're trying to research stuff like this, I mean, does this give us any insight into sort of the nature of information processing? I mean, first of all, maybe try and define what makes a quantum walk interesting compared to a classical walk, and does it make a huge difference? And is there any explanation or sort of a quick 5-second explanation as to why? This seems to be a powerful technique.
Yeah. So there's one phenomenon with quantum walks that we point to a lot that does give some sense for why they're faster, but at the same time, they are not the whole story. But it still might be useful. So let's say you have a one-dimensional line. Mm-hmm. So if you do a classical walk, say starting in the middle, and you just flip a coin. So if it's heads, you go right. If it's tails, you move left. And so you just keep on doing this classical random walk. And when you get after many, steps of this classical walk is a binomial distribution, right? So,
and this binomial distribution is where you end up after n steps.
Exactly. And so if you think about how quickly that binomial distribution spreads, it's basically how quickly that central peak spreads. Mm-hmm. And so that rate goes as the square root of the number of steps. Mm-hmm. So you just look at your at that width. So if you do instead a quantum walk on this one-dimensional line, instead of getting a peak in the middle, what you get are two peaks actually at the ends, and then in the middle it's relatively flat. Mm-hmm. So it's flat, and you get these two peaks. And these peaks move much more quickly. So whereas the middle, I don't know what I said earlier, it should be the square root of the number of steps.
No, that's what you said.
Yeah, okay, it's square root of the number of steps. These peaks for a quantum walk move at a speed that's linear in the number of steps. Mm-hmm. So it's a quadratic speed up in how quickly the probability or the wave function moves. And so that's one way of getting a sense for why quantum walks are faster, because they actually do spread more quickly on graphs.
Is there any fundamental, is there an intuitive reason you can point to for this, or is it just, sorry, you've got to look at the mathematics and this is just how it works?
I think it's because you think of it as much more like a wave that's moving. Mm-hmm. Like if you have even a water wave, you have a big crest, and it just moves across. So in this case, you have a quantum walk, you have these two waves that move, away from the center at speed that's linear with time. Whereas a normal random walk, it's kind of stays peaked at the middle instead of having this quick wave spreading.
And this obviously turns into something that's advantageous from a computational standpoint.
Mm-hmm. Yeah, it does. So I mentioned, for example, the ability to search for information on a graph if you've marked a particular vertex. There's other examples. So if you're trying to solve a formula that's based on the nans of bits, for example, So you can
This is
express
these logic operations, the not ands.
Yeah, so if you have some type of like, logic expression that you're trying to evaluate, it turns out that you can actually map this to a quantum walk on a tree, and you can actually find the solution to these logic formulas using a quantum walk. And so, there are different applications.
So you've obviously left Latvia, you've gone back home to the US, and now you're at the University of Texas Austin under the it is the newly formed group from Scott Aronson, who moved from MIT now back to Texas. So you're probably one of the first postdoc hires that he's made. This is a pretty, it's only been a couple of months since he's moved, right?
Yeah. It's been about 1 month. I mean, most of us started on the 1st of September. I got here a couple weeks early, so I've been here for almost a month, but officially we all started at the beginning of this month.
So what's the mandate? What's the structure for this new group? Is it just going to be sort of Scott's nature of complexity theory, or is it much broader than this?
Well, it's hard to know because I think the university does have the intent to hire more faculty members in the future, so that this becomes an actual research center and not just Scott's group, obviously. And so, depending on who they hire, that will dictate the direction of the group. In terms of what we currently have, I think Scott has a grant on quantum supremacy. Mm-hmm, mm-hmm. So there is some hope that, we're going to be doing things that are a little more practical, where we can develop problems kind of like the boson sampling that Scott came up with. Problems like that where we can try to come up with practical problems for, not universal quantum computers, but for, quantum computers in the next handful of years. Problems that they can do where they can demonstrate a superiority over classical computers.
So this might be a good segue, because now that you're talking about Scott's grant on quantum supremacy, I'm not exactly sure how much you work in this, but there was a paper from the Google group about 4-ish months ago or something like that, and some recent articles in the popular news about this idea of quantum supremacy with the small qubit quantum computers that they're developing now at Google. Can you give us a bit of sort of an overview of what this idea of quantum supremacy is, and if you understand it at all, maybe give us a bit of a run through about what's going on there?
Yeah, I mean, at its basic level is that it's very hard to build these quantum computers, and so to have a universal quantum computer that we can program to do anything we want might be further down the road, but in the short term, a lot of experimental groups are thinking that, within maybe 5 years, they'll have, quantum devices that are limited in what they can do, but maybe with, 30, 50, qubits. And so the question is, are there any problems that these limited quantum computers, limited both in what operations they can do and in their size, are there problems that they can do that classical computers cannot? And these problems don't have to be practical at all. Mm-hmm. Just some type of problem where we can prove that it's something that a classical computer cannot do. And so that's the idea, just to prove that quantum computers are actually better than classical computers, even if it's not something that is of interest as a problem.
But the point being that this is something that you can, pen on paper, and you can say definitely a classical computer cannot do this.
Yeah, or get it as close as we can. So maybe say that a classical computer cannot do this unless all these things that we believe to be true are actually false. Mm-hmm. So an example is like, a classical computer can't do this unless P equals NP, which most computer scientists believe is not true. Or, there's other problems like that, where there are different degrees of how outrageous it would be if that turned out to be false. And so in some cases, it's reducing problems to statements like that. Where,
and this is this wonderful world of complexity theory that the complexity theorists seem to understand very well, but the rest of us normal people really don't get at all.
Yeah. Yeah, so it's definitely something that I think this group will be working towards. Yeah, in terms of how much we've done, I mean, we just got here, so we'll see how it turns out.
I mean, how much in terms of what you've done in the past and hopefully what you're going to do in the future, how much of this is a motivating interest to you?
Yeah. I definitely think it's very interesting and fascinating, something I'd want to learn more about.
I mean, are you very much interested in this sort of complexity, this complexity theory zoo? Is this something that you really like to bite your teeth into?
Yeah, well, it's not something that I've worked on very much in the past. So my previous research hasn't really utilized these ideas from computational complexity. Mm-hmm. But it definitely is something that I'm interested in. So Scott's actually teaching a class right now on this, on both classical and quantum complexity. And so I've been attending that. I mean, yeah, we just started the school year. So, I'm hoping that as this school year goes on, that I'll learn some more and then we'll be able to come up with some interesting things as a group. Yeah.
So do you tie in much within, in terms of your collaborations or what's happening at UT? I mean, do you tie in much with the experimental teams? I mean, I see Scott's name on some experimental papers now and again. But is this now a driving factor within UT that you're now going to try and... I mean, I don't know if there's any quantum experimentalists or quantum computing experimentalists at Texas.
Not so much.
But sort of more broadly within the US and within the community worldwide.
Yeah. Well, I think the hope is with our project on quantum supremacy that we are working more closely with people who actually build these quantum computers, whether it's John Martinez from Google or whatever other teams are building these systems. I think the idea is to work more closely with them to understand what they can and can't do, and for us to come up with problems where we can demonstrate that a quantum computer is better. Mm-hmm. So that is the idea. How much of that will actually happen?
You can always cross your fingers.
Yeah,
it's not a huge leap to jump into this sort of area and this sort of field.
Yeah.
Now, I mean, we sort of move on a little bit now and sort of talk about more generally of what's going on in the field, and I usually start talking about the cross between academia and industry. Mm-hmm. Obviously, you're quite a young guy. This would be your second postdoc now at UT. I mean, how do you see yourself sort of, for anyone else who's sort of thinking about grad school, thinking about studying physics, mathematics, whatever, in terms of a field that's kind of emerging, in terms of how interesting it is to work on, and certainly the opportunities either in academia or pushing into a newly forming quantum industry? I mean, how does it sort of strike you?
Well, I'm actually very amazed with how much more industry is working on quantum information now compared to even 5 years ago. It seems like there are a lot more industry players now who are on board, and not just bigger tech companies, but a lot of small startups as well. So I think because of that, they are looking for people to hire. So in that sense, there is a growing job market for people who work in quantum information who want to go into industry versus academia. But I think also the job prospects in academia are, generally in academia, they're not great, but I think it's better in quantum information than it is in some other areas, particularly because there is so much growth in this. There's a lot more funding now. Like I'm sure you heard in Europe, there's a big EU funding push with €1 billion. Mm-hmm. There's recently a statement from a bunch of US funding agencies about the need to support quantum technologies, and in a lot of countries they're realizing that this is the future. And so as funding becomes more available, I think more universities will also hire faculty members who can be a part of that research. So
Was that a motivating factor for you? I mean, have you not quite made a decision yet in your own career about what's going to happen in the future, or you sort of decided, okay, I'm just interested in the research, so it's academia, straight and narrow?
I don't, what is it? I'm open to what happens. I think my natural preference is for academia. So I was actually a high school teacher before, in between undergrad and grad school. And so, so there is that part of me that really likes teaching and that likes working with students. And so naturally academia is, kind of the obvious choice. So I think probably for me, I'll pursue that, apply, see what happens. But if that doesn't work out, I'm also, very happy to work in, work somewhere else, work in, industry or something. Yeah.
I mean, in your contacts with industry or the guys that you've worked for and the groups that you've worked for, how much do you touch base with these sides? I mean, I talk a little bit with industrial players here and there and sort of, this is what we think you can do with quantum computers. This is why it's an interesting investment to utilize quantum technology. Considering you're much more on the fundamental side, I mean, is there that kind of contact with the industrial world that sort of, look, we don't know yet, but there are good reasons we believe as to why this is going to be, exciting and good and potentially lucrative?
Yeah, not so much, to be honest. I think being more on the fundamental side, maybe also being younger as a postdoc, generally they might, industry people might approach more senior researchers. Yeah, not so much. I mean, part of it is also I was, living abroad in Latvia for the past 2 years. And so I only just got back here recently.
Right.
That as well. Yeah, we'll see. I think part of it might also depend on, like I've said, living in Latvia, but in general, where you're located. So in Austin, there are a lot of tech companies, but there aren't any like quantum computing tech startups or anything like that. Versus in other cities, there may be a lot of, industry work in quantum computing. And then if you're in academia, they're more likely to have conversations with you. So yeah, actually, I've thought about it. If someone wants to start a quantum computing startup, Austin would be a great place because there's already tons of tech companies. And a lot of tech companies actually move from Silicon Valley to Austin. So that's actually...
I've heard that it's sort of turned into a Silicon Valley, sort of mini Silicon Valley down in Texas. And this is all, I mean, it's all not motivated, but certainly influenced by UT and Texas A&M and places like that. I mean, these universities trying to sort of incubate and encourage these kind of things to occur in Texas?
I guess I haven't been here long enough to see what programs they have for students to start companies. I do know that a lot of companies try to recruit our students here. I mean, here in CS, I see, companies hosting events, trying to recruit students, several times a week. So I think we're one of the top 10 ranked CS programs or something like that. So
in the US,
we are very, I don't know, but either way, I think it's quite good, right?
Oh yeah, I think if you're top 10 in the US, you're pretty close to top 10 in the world.
Yeah.
So I mean, how encouraged are you in that this stuff is going to push out into actual technology? Into this is not going to be pen on paper theory. That eventually we're going to have, hopefully, these quantum computing devices, and it suddenly becomes, physical tests of these ideas rather than just hopefully we'll write about the theory.
Yeah. Well, at least the work that I've done, most of it has been quite fundamental. So that work, it's not as, the chance of that making that into, say, industry applications, I think, is quite far-fetched.
Well, I mean, quantum walks have been, one of the primary demonstration tools. Particularly, I'm thinking in the space of linear optics. I mean, the guys at Bristol have been doing these. I think they're linear quantum walks, from what I can remember, like 20, 30 modes or something like that. How detached is that for something that really gets interesting?
Well, the thing is, most of the big players who are building quantum computers, so like, John Martinez's group at UC Santa Barbara / Google, IBM, they're all working on these, on these transmon qubits, and they're not really thinking about quantum locks in that sense. Mm-hmm. But there is also the sense that, any quantum lock algorithm can be turned into a normal, non-quantum lock quantum algorithm. So, but
both models are universal, so they can be converted into one.
Yeah. So even though you can convert a quantum lock algorithm into a normal, if you will, quantum algorithm, it's not the most natural for the current architectures that they have. And so probably the problems that they'll look at, initially at least, won't be quantum lock algorithms. Obviously once you have a full universal quantum computer, it won't matter. But at least initially, I think that makes my work a little more distant.
Mm-hmm, mm-hmm. Yeah. So we're getting close to sort of our 45 minutes, which is usually I try and max things out at about 45. So as I ask everybody, if you were to try and put your thumb on it for the next 5 or 10 years, I mean, what do you think is going to happen in the field in general, specifically related to your work and more generally globally in quantum technology? And sort of what would you like to see happen in the next 5-ish years?
Yeah. I think we'll have a quantum supremacy test I think we'll have that shown by then. Mm-hmm. I think a lot of people are saying that in that time we'll have big enough quantum computers, where if we do our job and can give them a good problem, that they'll be able to show that quantum computers are definitely better than classical computers. So that's something that I would like to see.
Do you have a favorite system?
I like both IBM and Google. I think they're
so superconductors.
Yeah. Yeah. I think they've made a lot of progress over time recently. So yeah, I'm looking forward to seeing what they do in the next 5 years.
So you believe quantum supremacy is something that you would like to see and is somewhat expected over the next 5 years?
Yeah, I'd say so.
You're not going to go, much more lofty and a lot more optimistic that, we're going to have a 200 qubit or 1,000 qubit quantum computer by that time, or a primitive quantum communications network that at least gets from, Texas to Arizona.
Maybe a quantum communications network. I mean, there's been a lot of work with quantum, trying to, there's a lot of work where people have sent quantum information over fiber optic cables. Mm-hmm. And then recently China launched something into space in order to do QKD over space, something like that.
Yeah, I think most people have probably seen the announcement where they sent the quantum satellite into space, yeah. And the Singaporeans about 6 months ago at least was demonstrating sort of quantum tech in space.
Yeah. And so I think we're going to see that in 5 years, a lot more space-based quantum technology. So in that case, we actually could communicate from, over these long distances from Texas to, where other people are. So.
Where other people are. Like Texas is in the middle of nowhere. Do you think that having the experimental systems would aid your work at all? I mean, if you had these things, sitting around where you could quite easily tell experimentalists, try this, try this, try this, without having to convince them for 3 or 4 years, would this actually help?
Only if the network is right. In the sense that I mentioned how a lot of my work in quantum walks has been studying what graphs those walks occur on. Mm-hmm. So, if it's a graph or underlying structure that fits very well with the things I work on, then sure, it'd be great. But if it's something that's totally different, then it might not work. So for example, IBM released their their cloud computer, the 5-qubit cloud computer. And so
Yeah.
people have been with that, but because of the way that the chip is laid out, you're not allowed to just do anything you want. If you want to do a CNOT, I think you can only do it with that center qubit.
Yeah, it's a central qubit. I mean, they had the guys on last week talking about that.
Okay. Yeah, and so essentially, how much I'll be able to do with the hardware is going to be based on things like that, on what it really lets me do.
So, I mean, if you were to wave a magic wand and be able to do anything, I mean, what would sort of be the size of the system that not so much would test ideas that you've had, but basically be a system where you could play around and get answers that you probably couldn't do on paper?
Oh, man.
Feel free to neglect the question if it's something you haven't even really thought about.
I think, I haven't thought about it enough to really give you a quick response.
No, that's no problem at all. So I suppose this leads into the last question as we're getting close to our time. Anything to plug? Anything interesting happening with UT, with this newly formed group? Anything you want to sort of promote or encourage people to look at, or do you need more students?
Well, we are definitely in a process of growing. So we are looking for students. If people want to visit, they're welcome to. I heard that Scott might even have funds for people to come visit. So if you want to visit and don't have your own funds, maybe ask Scott and he might try to hook you up. So I mean, we're in the process of growing right now, and there's a lot of exciting things that are going to happen in the future. So, I would encourage people to come by and to visit.
Yeah, well, I certainly would as well. I mean, I'll put all the links, obviously, to Tom's website below the video and onto our other accounts, and Tom's Twitter, which keeps us up to date with a lot of stuff happening in this little sub-area of quantum information, and obviously to the newly formed group at University of Texas at Austin. So just to close things off again, Tom, thanks a lot for your time and sitting down and having a bit of a chat with us.
Yeah, thank you.
Great. And so for those of you who are joining in live, thanks again. For those of you listening later, which is the vast, vast majority, again, thank you. Keep promoting this. As I said, we're on all of the major platforms now, whether it's iTunes, Google Play, Stitcher. They're all there. Just search up meQuanics. We are the only one. But please feel free to spread this and use this as far as wide as you can. Quantum information is growing as a field of research and a technology. We're now seeing investment across the board. The Canadians just announced an extra $70 million for Waterloo and IQC. The Australians just announced nearly $100 million in recent funding for quantum technology. So this stuff is picking up all around the world, and I would certainly encourage you to listen to this. And if you're interested in working on this and studying this, contact your nearest university. I guarantee you somebody's looking at this. So thanks again, everyone. Cheers.